And thanks for the invitation. So I will start with a few observations to motivate the content of this talk. This was life before AutoCAD. And this is life after AutoCAD. Computing square root of 2 is hard if you do it by hand, but simple if you use a pocket calculator. You just do it without thinking about it. Calculating mortgage amortization schedule is hard if you do it by hand, but simple if you do it with an Excel sheet. Why? Because the complexity of a problem is relative to our ability to decompose it by reasoning through simple concepts, encapsulating and abstracting away its technicalities. And if you automate the resolution of those technicalities, then you're only left with manipulating high-level concepts, and you're therefore free to perform tasks of significantly higher importance and complexity. The automation of calculus is an example of such a transformation. Question: is another level of automation and transformation possible for computational sciences and engineering? Well, the main purpose of this talk is to suggest that this question may have a positive answer. This answer is based on three observations. First, most problems in computational sciences and engineering can be formulated as that of completing a computational graph representing dependencies between functions and variables. Some of these functions and variables of the graph may be unknown, and by completing, I mean recovering the unknown functions and variables of the graph. Second, replacing the unknown functions of the graph with Gaussian processes and computing their map estimator given the data provides a simple and interpretable approach to completing such graphs. Third, since this completion process can be reduced to an algorithm, as one solves square root of 2 on a pocket calculator without thinking about it, one could, with the proposed automation, solve a complex CSE problem by drawing a diagram. Now, for ease of presentation, I will describe this underlying framework through examples, and I refer to this paper for the general abstract framework. Okay, so in the first example, we're going to frame the problem of solving and learning nonlinear PDEs as a computational graph completion problem. Now, there are essentially two main learning approaches to solving PDEs. Approaches based on artificial neural networks with physics-informed neural networks as a prototypical example, and approaches based on Gaussian processes with gamblets as an example. Although the Gaussian process approach is more theoretically well-funded and has a long history of interplays with numerical approximation, it was essentially limited to linear/quasi-linear/time-dependent PDEs. So what I will describe in the first part of this talk is a generalization of the GP approach to arbitrary nonlinear PDEs. And this generalization is a joint work with Yifan Chen, Bamdad Hosseini, and Andrew Stuart. And the method that we have obtained from this generalization has the following desirable properties. It is provably convergent for forward problems. It is interpretable and amenable to numerical analysis. You can use it to solve both forward and inverse problems. It inherits the complexity of state-of-the-art solvers for dense kernel matrices, and it can be used to develop a theoretical understanding of AN and Bayes methods. Now, this GP method can be applied to arbitrary nonlinear PDEs. But for ease of presentation, I will describe it first for the following nonlinear elliptic PDE, in which f, g, and tau are continuous functions such that this PDE has a unique strong solution. So the nonlinearity in this PDE is tau, which we assume to be continuous. And as an example, you can take tau of u to be u cubed. Now, observe that solving this PDE is equivalent to completing the following computational graph in which nodes represent variables and edges are directed and represent functions, with non-functions colored in black and unknown functions colored in red. This graph has only one unknown function, which is the solution of the PDE. Now, since this PDE is well posed, you may think that this solution is not unknown. But from a computation perspective, you can only compute with finite information, which means that you can only compute the values of f and g at a finite number of points. Therefore, from an information-based complexity perspective, U is as good as unknown, and the data is obtained by the computation of the values of f and g at a finite number of collocation points in the interior of the domain and on its boundary. Note that this data also corresponds to observations of subsets of the variables of the graph represented by these dash arrows. So for instance, this dash arrow represents pairwise observations of this variable and the right-hand side. Okay. Then the proposed completion approach is to replace the unknown function u of the graph by a centered Gaussian process with kernel k and approximate the solution of the PDE with the map estimator of that GP given the data, which corresponds to the GP satisfying the identities imposed by the graph or the PDE at the collocation points. In that expression, the variables zi1 and zi2 are the values of the intermediate variables of the graph at the collocation points xi. These intermediate variables are unknown, but their nonlinear combination through this non-function is known, as the value of the right-hand side of the PDE at the collocation point xi. Now, this map estimator can be identified as a minimizer of the following variational problem, where the quantity to be minimized is the RKHS norm of the function u defined by the kernel k, and the constraints are requiring u to satisfy the constraints imposed by the graph at the collocation points. Therefore, given a kernel k defined on the closure of the domain omega, the proposed approach can be summarized as approximating the solution u dagger of the PDE with a function un, where n stands for the number of collocation points, minimizing the following nonlinear optimal recovery problem, in which the quantity to be minimized is the RKHS norm of the function u defined by the kernel k, and the constraints are requiring u to satisfy the PDE at a finite number of collocation points xi. Note that these PDE constraints at those collocation points depend on whether they are located in the interior of the domain or on its boundary. Then we have the following theorem. Assume that the kernel k is chosen so that its RKHS space is continuously embedded in the subwheel space HS for some s greater than the dimension of the space over 2 plus the order of the PDE, which is 2 here. We need that condition to ensure that the PDE can be defined pointwise for the elements of that RKHS. Assume that the solution of the PDE belongs to that RKHS, and assume that the field distance between collocation points goes to 0 as the number n goes to infinity. Then, as n goes to infinity, the approximation un identified by our method converges to the solution of the PDE, where the convergence holds pointwise in a domain and in the subleft space HT for all t smaller than s. So this theorem is essentially saying that the proposed method is guaranteed to converge as the collocation points become dense in the domain if the kernel k is adapted in the sense that the solution belongs to the RKHS space defined by the kernel K, and that space has enough regularity to be embedded in a sublet space containing functions with continuous second-order derivatives. Now, this theorem generalizes to arbitrary nonlinear PDEs, and its general form is described in the following paper. Now, I will present the proof of this theorem, not only because it is simple, but also because it reveals a fundamental mechanism supporting kernel methods. And this proof also generalizes to arbitrary nonlinear PDEs. So first, observe that since U dagger solves the PDE 1, and since it belongs to the RKHS space defined by the kernel K, it satisfies the optimization constraints of 2. Now, since UN is a minimizer of 2, this implies that the RKHS norm of UN is smaller than that of U dagger, the solution of the PDE. Now, since this RKHS space H defined by the kernel K is continuously embedded into the sublet space HS, we deduce that the following norm, the following inequality holds for all functions V, which implies that the HS norm of UN is uniformly bounded in N by a constant C times the RKHS norm of U dagger. Now, since the sublet space HS is compactly embedded in the space HT for all t smaller than S, we deduce that UN converges towards some limit U infinity along a subsequence in HT and in C2. Now, since along that subsequence, the UN satisfies the PDE at collocation points, and since the field distance at collocation points goes to 0, as n goes to infinity, we deduce that this limit is a strong solution of the PDE. And since this solution is unique, we deduce that the limit is unique. And since it is independent of the subsequence, we deduce that the whole sequence is convergent. Okay, so the proof is fairly simple. Now, for the practical implementation of this method, this infinite dimensional variational problem can be reduced to a finite dimensional one by introducing the slack variable z corresponding to the values of u and of its Laplacian at the collocation points, and then minimizing over u before minimizing over z. Note that the slack variable z are the intermediate variables appearing in the computational graph. Now, given those variables z, the minimization over u is a linear optimal recovery problem for which we have the following representer formula, which I will now unpack. So in that formula, z is a vector obtained by concatenating the slack variables z1 and z2 corresponding to the values of u and of its Laplacian at the collocation points. To describe the other terms, I will write phi for the vector whose entries phi i's are delta Dirac functions at the collocation point xi, or delta Dirac function at the collocation point xi composed with the Laplacian operator. Kx phi is a vector whose entries are obtained by integrating the kernel k at the point x against the function phi. K phi is a matrix whose entries are obtained by integrating the kernel k against the functions phi's and phj's. Now, note that the entries of kx phi, of the vector kx phi, and of the matrix k phi are pointwise evaluations of the kernel k and of its Laplacian. So according to this formula, to identify this minimizer u, we only need to identify the slack variable z And these variables are identified by plugging this representative formula into the previous optimization problem, which then reduces to the following finite dimensional optimization problem over Z. Now, to solve this finite dimensional constraint optimization problem, we use the constraint to eliminate one of the optimization variables, which here is the vector Z2, whose entries are the values of the Laplacian of U at the collocation points. And we turn this nonlinearly constrained quadratic optimization problem into an unconstrained non-quadratic optimization problem. Now, to solve this unconstrained optimization problem, we simply use a variant of the Gauss-Newton algorithm. This algorithm is an iterative algorithm obtained by successively linearizing the nonlinearity tau around the previous approximation of the solution and by solving a quadratic optimization problem to get the next approximation of the solution. In practice, this Gauss-Newton algorithm converges in 2 to 7 steps, 2 steps for this particular nonlinear elliptic PDE, which means that the complexity of our nonlinear PDE solvers inherits the complexity of inverting dense kernel matrices. And we are currently adapting the algorithm found in this paper to do so in near linear complexity. Now, this Gauss-Newton iteration is equivalent to solving successive linearizations of the underlying nonlinear PDE, which is equivalent to solving the nonlinear PDE with a combination of Newton's iteration with the kernel or Gamlet method for the linearized part. The following numerical experiments compare the convergence of the finite difference method with the convergence of the proposed method using a Gaussian kernel. So you get convergence to machine precision, which is something that you typically do not see with ANN-based methods. Now, as mentioned before, this method and its convergence theorem generalized to arbitrary nonlinear PDEs. As an example, these figures illustrate the accuracy of the method for Berger's equation when using the following anisotropic Gaussian kernel, in which the length scale of space has been chosen to be smaller than the length scale of time to capture the underlying shock being developed in the solution. These figures and this table show the accuracy of the method for Eichhorn's equation when using a Gaussian kernel. And here our Gauss-Newton iteration converges in 6 steps. Now, this method can naturally be extended to inverse problems. As an example, consider the problem of approximating the solution, the unknown solution U, and the unknown coefficient A of the following PDE, given F and G, and given the values of U at a finite number of data measurement points, which are colored in pink in this figure. We have about 40 of them. Then the proposed problem can be formulated as completing the following computational graph, where A and U are the unknown functions of the graph, and the known functions are enforcing the structure of the PDE. Here, the data is obtained by the measurement of the value of U at the pink collocation points, the computation of the right-hand side F at the blue collocation points, and the boundary value G at the orange collocation points. The GP completion is then equivalent to recovering the solution and the coefficient of the PDE by minimizing the sum of the square of the RKHS norms with respect to 2 possibly different kernels, K and gamma, subject to the PDE being satisfied at a finite number of collocation points on the boundary in the interior, and also subject to a measurement of the value of the solution at the data measurement points. And as mentioned before, for the practical implementation of this method, you need to introduce the intermediate variables, Z appearing in the graph as slack optimization variables in the versional formulation of the map estimation of U and A. And these figures show the true and recovered solution of the PDE and the true and recovered coefficient of the PDE. The recovery is not exact because we have only 40 data points. The underlying Gauss-Newton algorithm converges in 5 steps, which means that the method inherits the complexity of inverting dense kernel matrices, so it can be made quite fast. Note also that we are solving both the forward and inverse problems at the same time, whereas the classical MCMC approach is to iterate between solving the PDE and solving the inverse problems. Okay. So we have seen that we can solve and learn PDEs by completing computational graphs. Now we will see that we can also turn system identification and digital or surrogate modeling into computational graph completion problems. We will use a nonlinear electric circuit as a simple illustration of this application, but evidently you can make the underlying example as complex as you want. In particular, it could be a full-blown climate system. So our next problem concerns the identification of the digital twin or surrogate model of this electric circuit whose RLC components are assumed to be unknown and nonlinear. We also assume that all the voltages and all the currents in the circuit to be unknown functions of time. Now, we run this circuit between time 0 and time 10, and at time Ts equals to S over 10, for S going from 0 to 99, we observe or measure a random subset of the variables representing the state of the circuit. This figure shows the values of the voltage V1, which is forcing the circuit, at times when those values are observed. So we make a total of 7 observations or measurements on V1. Now, given those measurements, consider the problem of approximating all the unknown functions, identifying the RLC parameters as a function of currents and voltages, and identifying all the currents and voltages as a function of time. This figure shows the values of the measured variables at time when they are measured. Observe that compared to a traditional regression problem, the data is too scarce to recover any of those functions independently from the others. To recover them, we have to exploit non-dependencies between functions and variables. To describe this, write X for the vector whose entries are the variables representing the state of the system. Observe that these variables are related to each other through non-functional dependencies given by the following equations, which are the Kirchhoff laws for this nonlinear electric circuit. Now, we can represent these functional dependencies between variables as a graph where nodes represent variables and directed edges represent functions, with unknown functions colored in red and known functions colored in black. And our solution is to replace the unknown functions by GPs and compute their map estimator given the data and given the dependencies. And these figures show the true and recovered functions using this approach. So the method works surprisingly well given that the data was quite scarce. Now, I will unpack this completion method, which again is the technical part that can be abstracted away and fully automated. To do so, I will formalize the representation of the data. Remember that we run the circuit between time 0 and time 10, and at times Ts equals to S over 10. For S going from 0 to 99, we observe or measure a random subset of the variables representing the state of the system, or a subset of the variables of the graph. Now, if for each one of those samples indexed by S, we write X as V for the value of the variable V in sample S, then X as V can be seen as the entry SV of some matrix X that has 100 rows because we have 100 samples and 14 columns because we are tracking 14 variables. Now, for each one of those samples, we only observe a subset of the variables, which means that we only observe a subset of the entries of that matrix X. Those entries are colored in white in the following figure. For instance, in sample 5, we observe the variable t, v1, i1, and l1 of i1. For sample 58, we observe the variable t, dv3 over dt, r of i3. And for sample 70, we observe t, v3, and i2. Now, our solution is to replace unknown functions by GP and compute their map estimator given the data. To describe this, write F for the vector whose entries are the unknown functions to be identified. Write M for the Boolean matrix whose entry SV is equal to 1 if variable V is observed in sample S, and 0 otherwise. And using Python notations, write X of M for the entries of the matrix X that are observed or measured. Note that the underlying problem combines a regression problem, that is recovering the unknown functions, with a matrix completion problem, that is finding the missing entries of that matrix X. Furthermore, it is equivalent to solving nonlinear systems of equations involving unknown functions and variables. Now, to approximate the unknown functions and complete the matrix X, we minimize the following loss, in which Z is our candidate for the matrix X. And I will now unpack that loss. The square norm of F is the sum of the squares of the RHS norms of the unknown functions with respect to the following Gaussian kernel. Note that this kernel does not add any prior information on those functions besides regularity. The L1 term in the loss enforces dependencies between unknown functions and variables. For instance, the term highlighted in green enforces the constraint that the variable representing the value of v1 is obtained by mapping the variable t via the unknown function v1. The L2 term in the loss enforces dependencies between known functions and variables. So for instance, this term highlighted in green enforces the constraint that the variables representing the values of I1, I2, and I3 must be such that I1 plus I3 minus I2 is equal to 0. And the last term enforces the constraints imposed by the data. Note that the term L1, L2, and L3 are soft constraints which can be turned into hard constraints. Now, to minimize the overall loss function, we minimize our unknown functions first. And since the problem is quadratic in these unknown functions, we have formulas representing those minimizers as functions of the unknown variables. So for instance, for the unknown function v1, this function appears in these two terms. Note that the overall loss is quadratic in v1, and minimizing v1 given the variable z is equivalent to solving a kernel ridge regression problem whose minimizer is given by the following formula. And if you do the same for all the unknown functions, then you reduce the previous optimization problem to one that depends only on z, and that you can minimize with variants of gradient descent or Gauss-Newton. Okay, so this was an application to system identification. Other applications include climate/weather modeling and forecasting, learning stochastic dynamical systems, learning Hamiltonian systems, dimension reduction, etc. The underlying principle behind those applications is always the same. You draw the graph, you replace the unknown functions of the graph by GPs, and you compute their map estimators given the data to complete the graph. Now, since artificial neural networks can be seen as particular instances of computational graphs, you can also use the proposed framework to analyze and generalize them. I will now illustrate this point for ResNets in the setting of the following supervised learning problem, in which you seek to approximate an unknown function f dagger given some input-output training data on that function. Then the ResNet solution to that problem is to approximate f dagger by completing the following computational graph corresponding to the composition of some function f with a deformation of the input space phi obtained as the composition of L functions written as the sum of the identity map with the displacement vi. Then the deep learning approach to completing this graph is to replace the unknown functions f and vi's by 1 or 2 layers neural networks and minimize the data mismatch with respect to the parameters of those networks. Now, instead of using the deep learning completion approach, you can use the GP completion approach. For this graph, this approach can be summarized as replacing the functions f and vi's by independent GPs and computing their map estimator given the data, which here is assumed to be noisy. So this little node represents noise variables being added to the output of the graph. Now, this is equivalent to recovering these unknown functions by minimizing the following loss, in which these are the RKHS norms defined with respect to two possibly distinct operator or matrix valued kernels K and gamma. Furthermore, if you choose those kernels K and gamma to be the following ones, then you recover ResNet with L2 regularization on weights and biases as a particular case. Now, we have the following theorem for the general case. As the depth L of the discrete network goes to infinity, the adherence values of the regressor obtained by minimizing the previous loss are of the form f composed with phi1, where phi is the flow map of the vector field v, t is a continuous parameter indexing the depth of the limit network, and v and f are identified by minimizing the following continuous loss. Note also that this continuous loss looks like the type of loss functions used in image registration to identify the best alignment between two images based on landmarks placed on those images. But here the images are replaced by abstract and unexpressed functions, and the landmarks are replaced by our input-output training data. Furthermore, we have the following representative formula for minimizers of this continuous loss. To describe this, write Q of t for the image of the input data x under the flow of the continuous graph at depth t. So these QTs are essentially the intermediate and unknown variables appearing in the graph. Then the following formula represents a minimizer v of the continuous loss as a function of the kernel k penalizing the lack of regularity of v. and as a function of Q and Q dot, which corresponds to the deformation of the trajectory defined by Q of t, which corresponds to the deformation of the input data set as it propagates through the continuous layers of the limit network. Now, if you take that formula and you plug it back into this continuous loss, then you get that the trajectory defined by Q of t must satisfy the following least action principle. Now, since we have a least action principle, we deduce that if we introduce the following momentum variable p, then the pair QP must be a solution of the following Hamiltonian system, which provides a constructive proof for the ODE interpretation of ResNets with train weights and biases. Now, so far we have looked at computational graph completion problems where the structure of the graph was given a priori. Question: can you use the data not only to compute the graph, but also to learn the structure of the graph itself? Well, I will now provide a positive answer to this question by considering the following empirical mode decomposition problem as formulated by Huang. In this problem, you observe a signal V on the time interval 0, 1, and you try to recover the modes composing this signal. You don't know how many modes are composing the signal, and the only thing that you know is that each mode is a quasi-trigonometric function with an unknown slowly varying amplitude and at an unknown slowly varying frequency. Now, we're going to solve this problem by learning the structure of the underlying computational graph from the observed signal itself. Our first step is to decompose the signal V into over finer modes living in the linear span of Gabor wavelets, which are essentially windowed trigonometric functions characterized by a time tau and a frequency omega. This can be summarized as completing the following computational graph, in which the unknown functions are those fine modes indexed by the time tau and the frequency omega. Now, to complete the graph, we identify the kernel of each fine mode by replacing the unknown functions, by replacing the unknown coefficients in front of the Gabor wavelets by white noise and by computing the covariance of the GPXC, the resulting GPXC indexed by time and frequency, which serves as a randomized surrogate for our fine modes indexed by the same tau and omega. And we're going to then you can approximate the fine mode VT omega by computing the conditional expectation of the GPXC tau omega, given that the sum of P's must be the observed signal V. Now, our second step is to quantify how much each fine mode contributes to the overall decomposition of the signal. This contribution or activation energy of each fine mode is quantified as its inner product with the overall signal, where the inner product is the one associated with the kernel K, defined as the sum of the kernels of the fine modes. And this is what this activation energy looks like as a function of time and frequency. And it essentially reveals the presence of 3 coarse modes in the signal. And these are the modes that we are trying to recover. From the GP perspective, this activation energy quantifies how much each fine mode GP has been activated by computing its conditional inner product with the signal V. This conditional inner product is also equal to the variance of the inner product between the fine mode GP and the signal V. And the sum of these variances is the RKHS norm of the signal. So you can think of this decomposition as a variance or RKHS norm decomposition. And this kind of decomposition is a very useful but little known property of additive kernels. Now, in our third step, these coarse modes are identified by using the GP activation energy to update the computational graph. The new element in this graph is the aggregation of the fine modes into 3 separate coarse modes. To perform this aggregation, we use the activation energy to partition the time frequency domain into 3 subsets, A1, A2, and A3. And we recover the coarse mode I as the sum of the fine modes indexed by tau and omega for tau and omega in the subset AI. And these figures show the true and recovered modes. So the method has near machine precision accuracy. And I refer to this book for further refinements of this approach to situations where the underlying waveforms are unknowns and non-trigonometric. And I will stop here and will be happy to take questions.